Hi, thanks. Yeah, so a lot of things already got mentioned, and as you heard there's a lot of engineering tricks involved in getting networks to run properly and getting the performance out that deep learning suggests or is known for. First of all, let me talk a little bit about generally there is a lot of types of architectures. So this is like just a chart of somebody compiling on how you can arrange neurons in order to get different architectures. A lot of them, for example, are not that frequent. So for example, neuron-Turing machine in medical image analysis. So some of these have recurrences in there, as you can see. Some of these have recurrences in there, the blue ones here, like recurrent neural networks or some concept of memory. And for the sake of this talk and the brevity of the 25 minutes we have, I'm just going to concentrate a little bit on elements or on higher level elements of feedforward networks as generative models and unsupervised learning are covered in other talks, and I want to step on their toes. So what we understand under feedforward network architectures is that typically what you see in yellow here is you have some form of inputs, some form of outputs in red, and then the green units basically encode or model whatever you've seen from data, and on the top row is somewhat what we consider what you've seen in a regression problem or a pixelized regression problem from the last talk. And within those, how you arrange these green units effectively will have a large impact on your performance, and also, so this is basically the gist of this talk is how do you properly arrange your architecture, and how do you make your optimization problem so well posed that you actually get good results. Quick recap about low-level operations. What you've seen here is what typically what we call fully connected networks, where you have a fixed size of inputs, like 3 here. There could be features, could also be time steps, could be however you design your input tensor to be. And this is could be a classification to like 2 output nodes. And in the middle, you have densely connected each of the inputs to each of the hidden nodes in the first. You can just because it's not clear often, you can basically express this fully connected layers with convolutions. As you can see, if you design a convolution that has spatially a 1 by 1 by 1, just sees one input at one time, it will basically transform this 1 by 1 with 3 features into 4 and extract 4 other features, convolutional features. So this would be the convolutional equivalent of this network. The difference is that if you would give it a larger sized input, it would stride along. It would convolve with each of those and give you a result at each location. So why is that important? Well, this fully connected architecture would see all the inputs at once, but convolutions would allow you to locally look at results, which is computationally a lot more tractable or when given large images. Assume like you have a 512 cubed CT, and then try and save all the activations and gradients, which is basically 2 times the number of weights you employ, a couple million in floating point. And you're going to store that memory somehow. If you want to copy back and forth through your GPU all the time, you're going to largely slow down your training, and you're not going to converge within reasonable time. So second element I want to talk about is nonlinearity. So as you see, these nice green nodes were considered neurons, some form of unit that it can extract something meaningful, right? But if you just daisy chain multiplications together, like just convolutions, it means you will arrive at a linear combination out of features, and it will give you a linear classifier, regressor, whatever. So typically after that you will have some form of nonlinearity, allows you nonlinear combinations of features, and thus allows you to fit a more complex classifier. So I want to just focus on a few of those here on the bottom ones, which is the sigmoid function, 10H function, and a ReLU. In 1996, these were mostly used as nonlinearities, and one of the big jumps that were done in like 2012 was employing one of the rectifier linear units here. What's the difference? What was the big improvement? Well, if you consider your network being multiplications, the further you go down, the larger your activations will be. At some point, when you compute gradients, you'll end up somewhere very far on this side or on this side, which means the gradient, as you can see, will approximate 0, and that means your updates will be small. So, and that's similar for both these. The ReLU, on the other hand, simplifies that as a very simple function. It allows you it avoids that problem and allows you to go more into depth, which allows you to extract more complex features and then perform better. And that was the entire thing out of that workshop that started a discussion on reviving neural networks. This ReLU has a particularity. As you can see, it's 0 when it's negative, which can also cause different problems. I'm going to mention a bit later. So I want you to think of network architectures not maybe on a low-level op kind of resolution, but think a little bit more higher. How can you combine basic ops together in the sense that they give you the best, actually the best features? And so I want to talk about what we call units, and particularly what we call here encoder units, which are basically just artfully arranging some of the low-level operations in order to extract features that benefit your performance. And I'll walk you a little bit through history and developments. I can't cover everything, but just the basic thoughts that went into designing those. And let's start off with a vanilla convolutional unit. So you have some X, some tensor going in. It will convolve, so it will basically multiply and extract some features. You'll have a batch norm, which will basically normalize your activations in order to make it more well posted training. A bit on more on that later. And then some nonlinearity. And then basically, if you daisy chain a lot of those together, you will have a neural network, a basic neural network. So the question is, there are some parameters in there, obviously, right? So in your convolution is how large should the kernel be? How many channels should I have? So one of the first networks, Inception Network, is Google in it, was trying to remove, again, the human as a source of error from the design of these modules, or from the design of the algorithm, effectively. And then what you see here is you have some X coming in, and if you don't know what your kernel size should be, you could basically try out all at once, or maybe pooling would be even better. Maybe you should just pool your results, and you can concatenate all these. And the idea is that basically, well, whatever doesn't learn anything will just generate noise, which will be concatenated and later on ignored, because it's just basically a weighted sum, the next convolution out of this. And so this is the basis for the Inception Network. Obviously, you have to go into breadth for this. So, and there were also some tricks in order to get these to optimize on a deeper level. So we've already heard about residual units. Just to have them here for completeness sake, you will have two feature extractors, so batch norm ReLU weight, batch norm ReLU weight, and the ability to skip them. Why? Just in case if these feature extractors at some point in your network will just not be able to extract anything useful, they will just generate noise if they would be in the network. So you give the network the option to just skip the entirety. So at the worst, you're just wasting memory, but you're not losing performance. And that had a large impact on results on the classification challenge, and you mentioned it. And I think most network architectures nowadays that are published use some form of residual connection or identity mapping. An extension of this was why do there always have to be two convolutional extractors and just one skip around it? It's another source of errors design. It worked well, just heuristically. why can't you not densely connect every convolution, every feature extractor, and then maybe just some of them might skip them? So this basically gives you densely connected convolutional neural networks, and they outperformed the residual connections beforehand. And lastly on this is also from the makers of ResNet, is trying to remember the initial Inception Network, where you go into breadth, where you're basically trying to have different options at the same time on one feature scale, on one part in a network. Well, this is trying to do two things. It will give you a skip connection from ResNets, and it will also give you the breadth of the feature extractors. Basically, this resembles what within each of the neuron you will have a tiny network that extracts that. So each of them can be considered like tiny neural networks. So it's basically a network and neuron concept, if you think about it. And lastly, this is one of the most recent developments, squeeze and excitation networks. It just basically take a standard network and you attach a module which you call squeeze and excitation units. The reason for that is if you have a few convolutions and you transform them from filters to filters and you multiply and you apply nonlinearities, one thing doesn't happen, and there is no connections between spatial locations, like in your kernel, within your kernel. And what you basically do here is you have some form of some form of disentanglement, and then another set of filters that will allow to spatially connect or make spatial connections, and a compressive factor, and that will basically like restore your old inputs so you don't get like engineering issues on attaching more of those. But basically it's just an addition to any of these extractor units, so you can attach them to ResNets. In this paper they were attached to the ResNext, so the one I just talked before. And this is, yeah, I think the winner 2018. And so the second part of high-level elements I want to talk about is transition units. So think about it like this. You will have one resolution scale, the image you put in, you'll extract a series of features. And you would want to obviously look at different resolution scales. We heard that in the talk before. So we call these transition units generally, is how do you transition between different scales. And also just to recap, some input tensor, you will have a pool size for max pooling or for average pooling, and you compute the maximum activation or an average activation. And that allows you to somehow downsample your tens of activations to something to look at more global context, to look at more higher level features. Just want to mention, because they're very common, strided convolutions, instead of you applying some operation that's predefined, you can also just design a 2x2 convolutional kernel that strides with a certain factor, and it effectively will learn the best downsampling for you. So this is my preferred, so if I build networks, this is my preferred way of doing that. And I think most high-performance networks do. So in order to show you that these theoretic improvements actually have an effect, we just designed a small regression experiment. It's not medically useful, but we used our library for that. We have a regressor in there with a standard ResNet implementation that just learns from these very coarse 2 millimeter brain images to regress the age of the patient. And so one of the things I was talking about with Relo before, I'm come back to this, is that one of the problems is that if you at some point reach 0 activations, your gradient will be 0, and that means your neuron dies off at some point. So a slight modification to Relos to rectify linear units as nonlinearity was actually having adjusting the slope a little bit by a factor alpha here. And if you run that through a relatively small network architecture in order for that regression experiment, you'll see you'll get quite some improvement out by just switching out one of these small low-level ops towards something that's a little bit more up-to-date. So if you compare all these same network size, roughly same transition units, the only thing that's switched out are these higher level modules. Is if you use residual units, dense units, resnext, or squeeze and excitation resnext units, you see that your validation or test error of the approximation, so this is the database statistics, yeah? So we are well within something meaningful that we predict, we're not just predicting means here, decreases the further you go along in time and methodology. Now the interesting part here is that you basically, your dense net gives you a little bit worse results than your residual network. But if you consider the number of weights that are actually used here, the ResNet in that sense is a lot more expressive, so this is very expected. But if you consider, I think 4.8 or something on 20,000 scans I've seen a paper recently, like last year or something, so it's good values actually, like good results. 4.1 is quite good if you consider the number of weights, so the ResNext kind of setup that's more going into breadth allows you to actually save a lot of memory. That might be interesting for a lot of people here working on CT or high resolution images or stains or on large scale 2D images. Let's talk a little bit about training these things and optimization. It's really hard to go in within 20 minutes through everything, so I'm just gonna again point out what the major improvements were and what you gain out of just using some of these things out of the box. Let's talk about optimizers. So we all know we can optimize the weights with gradient descent or with stochastic gradient descent by using mini batches. We'll have some update, and we know we have a learning rate that scales that update linearly. Basically, momentum and Nesterov momentum allow you to have some form of history. So you go back in time, you have the last update included, and the velocity of how far you do that. It's actually a slight difference in ordering, but it makes a difference applying these. You can try them out yourself. Adagrad accumulates gradients beforehand and adaptively updates each of your weights individually. And that helps a lot when you have features that are very frequently seen and you do have some features that are rarely seen, and these edge cases get a lot of improvement from using adaptive methods like the ones on the bottom. So at a delta, RMS prop limit the amount of gradients they accumulate to a window, and Adam here, which I typically suggest because it's the easiest one to use out of the box. Additionally, ADAM stands for adaptive moment estimation, I think. Uses also the concept of velocity and the concept of past gradients and adaptively updating the weights. So typically I would suggest, if you start off, you have no idea, pick Adam, pick default learning rate, see what you get. Very important, just as a trick, there is an epsilon parameter. You might want to adjust this for some problems in order to avoid getting huge loss spikes that correct itself after a while. This is if this value here is too small, you might get too large numbers. As you can see here, this is how adaptive methods and momentum methods behave in order to get to the optimum. You see the red one, gradient descent here linearly steps towards this very slowly, but you might not have the time to actually let it converge, or it might converge in some absolutely unreasonable time. You see momentum methods overstepping largely into the old direction and then having to, along the loss manifold, having to return and go in another direction, and you see that adaptive methods basically very quickly step towards that optimum and then slowly converge towards that. Just because this is important, it's just a practical schematic that I like very much. It is how should my learning rates look like? Is it useful? What is a good learning rate? What is problematic? Obviously, if your validation loss increases largely, what you do is overfitting. If you have a good learning rate, and at some point it looks like your loss is converging, it actually means that the loss value itself might not look like it's doing something, but very refined, detailed, small changes often make a large impact. So I suggest you to let this converge properly and not cut it off whenever you see that the loss is at some point stagnating. So it helps a lot to, what we do is we say, here's 100,000 iterations, let this run to the end. You can always then afterwards see if you can save a little bit of time on recomputations by cutting it in half. But typically we've seen like that problems that are very subtle require a lot more time than you'd think for converging. So one of the things in order to make networks behave a little bit more better during training is, as I said, if you daisy chain a series of multiplications behind each other, you'll end up with activations that are quite large. And what does that mean? Well, that means that you're suddenly in the saturation of your nonlinearities very quickly. So one of the coolest innovations were from 2015, I think, was batch normalization. Basically, from each mini batch, you can compute means and variances, and you normalize your activations. But in order to not just have every input to a nonlinearity completely normalized, you'll have a shift and scale factor here that you can learn. This is this gamma, and this beta basically avoids you having a bias. So this comes for free. Batch normalization has shown that you can actually let very large and very deep networks still converge. So I think the deepest network currently is a ResNet with 1,001 layers, which we'll never achieve in the near future in medical image analysis, but still. The very last concept I want to talk to you about is class balancing. It's a major issue for medical imaging in particular because some of the cases are very rare. Diseases are rare. There's two means of how you can tackle this problem. The problem is generally if you see too many cases of one class, you will bias your output towards, like your network predictions towards that class. You can tackle this problem on two sides. You can tackle it on the sampling side or on the loss side. Sampling side would be very simple. Assume that this is your initial distribution and you would want to have something somewhat more balanced, and it's approximate balanced. The problem is not between 20 and 80%, the problem is between 0.1 and 99.9. Yeah? And this is often the case. So you have several options. One is you oversample the underrepresented class, or you undersample the overrepresented class. Each one of them has a particular advantage and disadvantages. In the disadvantage being if you oversample a very rare class a lot, you bias it towards that one example you showed the network repeatedly. And if you undersample, obviously that means that you're not going to see the entirety of the data on another class. Other solutions assume that you just heuristically determine a number and then sample as many times as you need. It's a balance between both, but your mini batches ideally are somewhat balanced. And another way, and you can combine these by the way, another way would be modifying a loss function that is basically often a pixelized loss function. So it allows you for each pixel to adapt the computed loss and the average that you accumulate afterwards by a weighted average. And that weight you can determine on however you like. One inherent way of doing that is just using a smooth dice coefficient as a loss, because it's already a per class loss and you average across all classes. So you reduce the problem inherently. One of the more common used losses is a median frequency reweighted loss, where you track the frequency over time of each of the classes, and then you basically just multiply and reweight before you do your average of your total loss. Yeah, so that's the end of my talk. Hope I was quick enough on this. Some resources on DLTK, if you want to see that example, you can download it and run it. It's all And I want to actually mention these two upcoming events that we are involved in. So I hope to see you at each one of those here, middle 2019 in London at Imperial, and then MedNIPS workshop at NIPS. Thanks.